In this question, we're told that benzene reacts with an organic reagent in the presence of a halogen carrier to form phenylethanone. So here's the sort of overall reaction. We're going from benzene to phenylethanone. So what's changing? Well, we are going to be swapping out this hydrogen for this carbonyl group. And we need to think about how that's going to happen, and this is an electrophilic substitution mechanism. So what does that mean? Well, we know that we're substituting this hydrogen for this group here, this ethanone group, and we can figure out that this has to be by an electrophile because we have an electron dense system here. So this is only going to attack something that is positively charged. And in the case of benzene, it needs quite a strong electrophile, something that actually has a full positive charge rather than just a partial positive, because the benzene ring is so stable. The molecule is much more stable than you'd expect. This is part of the syllabus earlier on in comparison to cyclohexatriene. Benzene is much more stable than that, and that comes from this delocalized ring system. So we need to think about which of these options, which of these reagents is going to be able to form a positively charged cation. So first of all, it's going to be good to draw all of these options to see which one is going to work. So first of all, we have ethanol, then we have ethanal, then we have ethanoyl chloride, and finally ethanoic acid. So we need to ask ourselves, how do these form carbocations? Well, they react with this halogen carrier that was alluded to in the question, which is usually something like AlCl3. And that pulls off an atom, a leaving group, and leaves behind a carbocation. So we know that we want to form this carbocation to give us this group. So when the ring attacks the carbon, we're left with this group on here after the hydrogen falls off. So the first option we can eliminate is ethanol. Oh, I've made a mistake drawing ethanol there. It's one too many carbons. So ethanol isn't going to work. It's an alcohol. It doesn't have this carbonyl group. It's not going to be able to form a stable carbocation. And we're left with these three carbonyls that all have different groups on here. And one of these is going to have to act as a leaving group. So if we think about what the leaving group would be for these three compounds, it would be H minus, Cl minus, or OH minus. H minus is by far the least stable of these options. Hydride anions do form sometimes, but really not very commonly as a leaving group. You should only really be seeing these when they're sourced from something like sodium borohydride as a reducing agent. And then we're left between chloride and hydroxide anions, and we need to think about their relative stability. So whichever negative ion is more stable is going to be the better leaving group and will be more likely to form this carbocation that we want to. So the best way to think about this is quite complicated. The best way to think about it is to think about the acids that would form these conjugate bases. So if we have HCl versus H2O, both of these just adding a proton. If we think about HCl, it's a strong acid that will fully dissociate into H plus and Cl minus, whereas water is weakly acidic and will split into H plus and OH minus in equilibrium rather than fully dissociating. So the answer here is going to be C. Just to clarify, the reason that this is more stable is because we know that the acid more readily dissociates when we have a more stable conjugate base.